The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to the Structural Simulation from Hand Calcs to Nonlinear webinar. My name is Sean Bentley. I've been with Decide Solutions for about 11 years now as an applications engineer. My primary roles are to do technical support, training, and also a variety of other miscellaneous things, but they all sort of fit under one category. It's to educate our customers on SOLIDWORKS and primarily simulation. In this presentation, I'm going to start off by outlining a couple of these simulation tools that are available in different SOLIDWORKS and simulation suites. Then I'll pick apart a couple of these tools, specifically a structural analysis line from SimXpress up to nonlinear. I'll talk a little bit about what we mean by nonlinear, compare that to linear analysis, and show some animations illustrating these ideas. Then we'll move into an example that where we'll start at a hand calculation and compare results of SimXpress, static for assembly, and nonlinear on the same kind of problem, different approaches depending on which package that you currently have. For those of you who have SOLIDWORKS Standard and SOLIDWORKS Professional, you can use Simulation Express and also Basic Motion. For those of you who have SOLIDWORKS Premium, you'll have access to an upgraded version of SimXpress, something called static analysis for assemblies, and also an upgraded version of basic motion, a time-based rigid body motion. And for some of you who have some of the simulation structural analysis packages, Simulation Standard, Simulation Professional, and Simulation Premium, you'll have access to a much wider range of structural analysis tools. Specifically, the ones I'll be referring to are the nonlinear and static for assembly and the SimXpress that I mentioned a moment ago. So this line here. This line that we're talking about is static analysis. So we assume that the loads are applied slowly with each of the analysis types that we're going to be talking about in this webinar. So to compare the different types of static analyses to each other, SimXpress allows you to do analysis on single body parts only. So no assemblies, no assembly modeling. It has to be single material, single body part. Variety of other limitations also listed here, but I'll sort of summarize them with one main point in a moment. Compare that to some of the relative limitations of static analysis for assemblies. In this analysis type, we have to make assumption of linear material, and we can't do any load sequencing. And nonlinear doesn't have, the nonlinear analysis on the far right doesn't have these same limitations. So if I really had to boil it down to something simple here, Simulation Express is purely linear analysis. Static for assembly allows you to incorporate some nonlinearities, so it's partially linear, more on that in a moment. And then nonlinear gives you more or less full-blown nonlinear capabilities. So really to talk about this idea of something being partially linear, I need to talk about what are we really getting at when we're talking about linear analysis? Do we mean constant load? No. When we talk about linear analysis, do you mean load in one direction? That's not it either. It's another common answer that I hear in many of my training classes. And then do we mean a single load or a single fixture? Is that what we mean by linear? No, not that either. Really what we're getting at when we say linear analysis is loads are proportional to displacements. So in other words, if I apply some load magnitude, I'll get a concrete displacement answer on all the nodes essentially in my model. But if we just look at the maximum displacement, for example, that also means that if I apply any other load, the displacements will fall on this line if it's truly a linear analysis. So here we have the loads being proportional displacement. You double the load, you double the displacement, triple the load, triple the displacement, etc. Very simple, predictable relation. So when we say something is partially linear, what do I mean by that? Well, really, I mean we can account for some nonlinearities and not others. There's three primary types of nonlinearities that we need to talk about: contact nonlinearity, geometric, and material. So discussing these, and I'll show some animations of each to really clarify. Discuss contact nonlinearity. This animation should illustrate what we're talking about when we're mentioning a contact nonlinearity. There's three types of contact nonlinearity: no penetration, shrink fit, and virtual wall. If you select any one of these three contacts, you'll have very similar behavior. Whenever you introduce a nonlinearity, it makes the solver take a lot longer to run. You might have to do some more troubleshooting, more stability issues. Okay, so be hesitant whenever you have to introduce these contact types. And the reason being is if we take a look at that force versus displacement curve to see if it's proportional, in this model it's not. You see it's initially proportional, but then there's a kink in the displacement curve. As soon as it makes contact, it sort of stiffens. So this creates a nonlinearity, and the study has to run iteratively rather than in one single step. So any one of those three contacts, no penetration, shrink fit, virtual wall, will introduce nonlinearities. So the second type of nonlinearity, geometric nonlinearity. This one's a little trickier to describe, but I'll summarize it with some animations that illustrate these three main points. If you have something that's geometrically linear, you'll see straight line deformations. Also, large rotation is prohibited. That also violates that straight line deformation idea. And really the main point here is that the stiffness is constant. So these 3 points sort of overlap, but the animations will show each one individually. So to look at the straight line deformations idea, here I have, if you think of maybe something like a hose clamp, if I fix one end and I twist the other end, I'm going to twist this thing around, and I want it to try to make contact back with this end. Okay, so I'm applying this twisting load to it. The displacement direction will initially be pointing straight downward, but it should curve around. If I run this as a linear analysis, which assumes straight line deformations though, here's the kind of result I get. If you follow these nodes with your eyes here, I've drawn a line to illustrate that each node follows a perfectly straight line when you assume linear. So obviously this answer is wrong. It's not what it does when I apply a twisting load to the end of it at all. However, if I run it as geometrically nonlinear, you see I do get more seemingly correct behavior. It does follow the curved path. So looks like geometrically nonlinear gives me the right answer. Compare this to compare the results between linear versus nonlinear when we're looking at rotations. Here I'm trying to twist the end of this bar. You see, it initially looks like it twists, but since all the nodes are forced to follow a straight line, it can't really twist around an arc. It has to go in the straight line pattern. Compare that to geometrically nonlinear, which we do get more or less the correct twisting behavior. You might have seen an error message when you're running static studies. Something about large rotation has been detected. It's warning you about geometric nonlinearities. Then finally, talk about stiffness changing. This happens a lot in thin wall structures. So if you have a sheet metal part surrounding a hopper that's going to be filled with plastic pellets or like a milk jug, anything that's going to be filled, a container that's filled with something that will exert pressure on those outer walls, this kind of behavior you may need to account for. So any thin-walled structures. So this behavior I'm talking about is stiffness changing. So when I put if I put a pressure load on that thin wall, a geometrically linear solver will give me this kind of answer, compared to a geometrically nonlinear gives me a much smaller answer, much smaller. So it's due to membrane stiffening. If I look at the curves of how the result progresses in both cases, you can see the pressure that I'm applying versus the displacement. As I increase the pressure, the linear, it just assumes the displacement increases linearly, whereas the nonlinear shows a stiffening effect. It develops what we call a membrane stiffness. If I zoom in on this initial point, you see both curves match initially. They both follow the same sort of line, but the geometrically linear just sort of extrapolates from there simply, whereas the nonlinear will update the stiffness as it goes along. So finally, the last type of nonlinearity, material nonlinearity, is a little bit easier to describe or at least point out. This so for material nonlinearity, have you ever noticed this little SS next to some of the materials in SOLIDWORKS? That doesn't mean stainless steel. If I go into the aluminums folder, you'll see SS next to some of the aluminums as well. What it really means is stress strain. It means that these materials have a stress strain curve available to you. This will relate the stress, or in other words, the internal pressure, the forces, the internal forces in the structure. It'll relate that to the strains or the elongations. Linear problems will assume that relationship is linear, it's a straight line, whereas nonlinear will be allowed to use this curve so long as you select one of the available nonlinear material models. So here's an example that shows some yielding, which is it's using that stress strain curve. The region on this wrench that I'm bending, you see this big white region, that's the yield region here. And I'm going to look at the stresses that develop through this thickness here, negative and positive bending stresses. And they'll look something like this. Pretty simple growth of the stress, simple linear growth of it, predictable, up until we get to that yield point, which in this case is around 90. Once I get up to this 90 mark here for the stress, it'll start yielding. And then the relationship gets more complicated, more complex, or nonlinear. So a static study cannot, a linear study, I should say, cannot account for this nonlinearity. So those are the three types of nonlinearities. And now to come back to our main point here about simulation express being linear, static being partially linear, and nonlinear being full-blown nonlinear, we can compare which kinds of nonlinearity each one of these studies can account for. SimXpress, being a purely linear study, cannot account for any of these three types. Compare that to the partially linear static analysis, we can account for some contact nonlinearity. And if I take a look at this animation, though, it looks a little funny, though. Let me zoom in on it. Doesn't it look a little strange? So you see it, the static analysis, it will report the correct final position of the assembly. Okay, but it won't save all the results of all the intermediate steps leading up to that final result. Okay, so you get the behavior that looks like this, where it's just interpolating between the initial position and the final position if you were to look at an animation. So it kind of does the trick. It gives me the correct final answer, maybe, if that's all I'm interested in. Then, but look at this one here. Again, it seems to predict the correct final position, but all those intermediate positions are sort of lost. And if my goal is to try to figure out what's the contact force required, it sort of loses that result as well, because at the final position, the contact force should theoretically be close to 0. So that one, there's some ways we can kind of trick it to work to give it the answer we're looking for, but it doesn't quite do the job. But again, we can kind of get it to work, but it will have to be a bit creative. So again, we can handle contact nonlinearity somewhat in static analysis to a fair degree. As for geometric nonlinearity, the options here are fairly limited. Basically, you can turn on this checkbox and then sort of cross your fingers, hope that it'll be able to account for the geometric nonlinearity that you're hoping to account for. And it will account for the three types I had mentioned earlier: stiffness changing, straight line deformations, rotations. Okay, it'll help out with those cases, but if the solver fails to converge, it'll just give you a solver failed message without much extra help for troubleshooting. And finally, material nonlinearity, nothing. We can't do any of that in the static analysis for assemblies. Now let's compare it to the full-blown nonlinear. We can handle all three of these reasonably well. If you look at these contact nonlinearity cases, see these same animations from before. Here you do get correct behavior as well in the intermediate steps, and using the and we'll even be able to get the forces, the amount of force required. If I want to push this clip into place, here's the kind of force required. See, initially it's 0, and then as soon as it gets in this region here, that force grows up to a maximum and then actually drops off a bit till when the clip is actually in this lowest position. Then the geometric nonlinearities, we have a lot more options. Remember, with the static analysis, you only have this little checkbox you can turn on, but with nonlinear, you get a lot more control over how it's going to run the calculations. Okay, you can have it update the load direction with the deflections, and you have these load increments that you have direct control over. And then as for material nonlinearity, we can account for the stress strain curve using these different material models. So next, what I'd like to do is walk through a specific example on the snap clip here. Again, the goal of these studies is to try to estimate or calculate the amount of force required. If I were to push on this end of it on the right, if I push on that, how much force is required to get this to snap into place? So it's about overcoming this initial hump. That'll be the primary determinant of the snapping force. Once I get over that, I think the force will be relatively low to get it to slide and then snap into place ultimately. So it's really about estimating that force here to get over that initial hump. So I'll use several different approaches depending on which level simulation tool that you currently have. So if you have just SOLIDWORKS Pro or SOLIDWORKS Standard, you'll likely use a combination of Hand Calcs and SimXpress. If you have Simulation Standard or SOLIDWORKS Premium, we can use static analysis for assemblies to help estimate it. Or if you have Nonlinear, we can be much more direct and get a good estimation of that result. We'll compare the answers from these different methods. So starting off with those of you who have SOLIDWORKS Standard or SOLIDWORKS Pro, we'll try the hand calc coupled with SimXpress method. So as for a hand calculation, you can look up equations online for things like the bending stiffness of a beam. So let me go back for a moment. You see really the key to doing this simulation study is to figure out how easy is it to bend that little arm, this little arm here. How easy is it to bend that downward? Because the ease in which I can bend that down is going to have a direct relation to how much force I have to apply to push it into place. So it's going to be coupled on that behavior. So I'm going to look at this bending equation, which incorporates things like the material constant, the length of the beam, the load I'm applying to the beam, and also the inertia, the moment of inertia. So that's dependent on the cross section. How thick is that cross section? So to estimate these things, here I've got a quarter model set up on the clip that I'm going to be sliding in place. Here's that beam. But I'm going to look at the full section of the beam. And you can use this tool called section properties. You guys ever used this tool before? If I click on section properties and I click on this little cross section I've made here, it'll tell me directly what the moment of inertia is on that cross section. It does the integral for me of figuring out that moment of inertia around this x-axis here. So this 119.4 is going to be that I in that equation from a moment ago. Also, another thing I want to try to figure out is when I apply that load, the maximum horizontal force is going to be dependent on this triangle here that I've sketched in. So I'm assuming the contact force is going to be perpendicular to the surface. And you can see I've broken that contact force up into two components. A vertical component, which I'm assuming is linearly proportional how far up I'm moving, how far down I'm bending this thing essentially. And then also this horizontal component, which seems to max out. See how it shrinks when I get over here? It grows and then it sort of shrinks again when I extrapolate over here. There seems to be a maximum point. I have this line over here also illustrating that, how it's growing and shrinking. So it seems to be a point where it hits a maximum. That's going to be my maximum lateral force that I'm going to need to use in order to that's going to be the maximum horizontal force I'm going to need to apply to overcome this contact force that's pushing back on me. Okay, so the main point here is you see how creative I sort of have to be to try to estimate where that final contact point is going to be. It looks to me that it's going to be right about here according to this estimation. And by the way, this assumption doesn't take into account the fact that this will bend downward and sort of changes this angle of this beam a bit. So and maybe significantly, maybe not. I'm assuming that that's small. So it looks like that maximum force is going to be somewhere right around here. Okay, so that's where I'm going to model, if I discard these changes here, that's where I'm going to model this little plate. I'm going to cut off the rest on the right side of the beam for a little bit later, but that's where I'm going to model a place where I can put forces in a moment. And that's where I'll measure the length of the beam as well. So for the hand calculation, I've got the length. I'll just apply a unit load. I've got the modulus of material I plan on using, and then I also have the moment of inertia. So I come up with a hand calculation that looks kind of like this. Anyway, I'm not going to go into detail here, but you see the compliance I came up with, or the stiffness, the inverse of stiffness, and based on that, horizontal triangle and that horizontal proportional force, I get 9.8 newtons. I'll use that to compare later. By the way, that's about 2 pounds. Okay, so about 9.8 newtons. Now let me compare that to a SimXpress study. If I were to use SimXpress to estimate that compliance, rather than trying to use that beam calculation, here's what that might look like. With SimXpress, let me turn off the full-blown tool here for a moment. With Simulation Express, I'll tell it to show me the maximum displacement when I apply a unit load to this. I'll put my fixtures. See, I've modeled in a portion of this structure over here. I'll just fix these outer faces because I'm assuming the rest of the structure is fairly rigid compared to this beam. I'm even tempted to just fix the side of that beam, but I want to incorporate some of the local bending that happens over here too that my hand calculation couldn't account for. So this might underestimate the stiffness compared to that hand calc, or maybe the hand calc overestimated the stiffness because I was only measuring that length up to this point here. So that looks good for my fixture. For the load, I'll put a load on top here, and that'll just be a unit load, 1 Newton. Material's already been applied, and I'll run the simulation. The deformation pattern looks okay to me, and now I'll look at the displacement, which is the primary result I'm interested in. And you can see the maximum displacement, thankfully this note points it out, of 0.1336. Now I say 0.1 because it's E-1 scientific, so you have to be careful with that. So 0.1336 millimeter. So if I compare that to the hand calculation I had a moment ago, so that means that's 0.1337 millimeter per Newton because I only applied 1 Newton. So that's my compliance. And you compare that to compliance from earlier, say a little bit different. So then the resulting force I get from that same hand calculation is a little bit different as well, 9.8 down to 8.6. So this has a big dependency on this little length variable. Like the length is a little bit longer in this case on the Simulation Express study because I included more of the surrounding structure. And you can really see the impact on the hand calc. If I just change this length by a couple millimeters instead of assuming 50 millimeter, if I change it by just a little bit, like to 55, that increases the compliance and drops my force way down. Now it's underneath that force. So it's important to get this number sort of right for the hand calc. It's one assumption that's my result's very sensitive to. It's length to the third, so no wonder. All right, so for now though, I'll accept these as my comparisons because I don't really know better what length to apply there. So 9.8 and 8.6 I'm going to trust a little bit more, I think. But let's move on to some higher level simulation. Let's see how these results compare with, say, our Sim Standard or SOLIDWORKS Premium tools. If you have SOLIDWORKS Premium or Sim Standard, you'll have access to static analysis for assembly. So all right, just looking at the animations, it doesn't look too promising, but there are ways that we can approach setting up this study, which let me show that now. So here I have a quarter of the assembly modeled, and I'm going to model it in such a way that they're initially touching. If I don't model them where they're touching, then you get some instability, solver failed issues. So just due to the static analysis having to apply a load, and then the thing accelerates off in outer space, so to speak. So we're going to stabilize it by just making sure they're initially touching. I'll turn on my simulation add-in. And we'll just set up a brand new static study from scratch, show you a couple of the assumptions I'm making. So start off with the material. With static analysis, I have to do a linear material, so I have to assume that this plastic I'm going to select has a constant elastic modulus, or a linear material behavior. Now for the connections, I want to make sure I turn off this bonded contact. I don't want anything to get bonded together, and instead I want to incorporate some contact nonlinearities, such as no penetration contact. Specifically, I'll select these faces here for what I'll call the source, and then for the target, I'll select these faces here. I'm going to turn off a couple of the faces. I don't need to incorporate these couple of faces as the target. All right. So that incorporates some contact nonlinearity, which we weren't capable of using in the SimXpress anyway. Now for the fixturing, since I have modeled this as a quarter model, I'll apply some symmetry boundary condition here to these split faces. I'll make sure I grab all of them, even though I see the preview already. I'll grab all of these side faces, including these bottom ones. Now also another fixture, I'll make sure I fix one side and then I'll put a load on the other side. So maybe I'll fix this component, similar to what was going on in those animations from earlier. Then I'll apply a force onto this face. And it's tempting. Maybe I'll start off with 1 Newton, because if I do 1 Newton, that should not be enough force to cause this thing to slide. And as I increase the load, I'll experiment with increasing this load and see the kind of result behavior I get. Okay, but starting with 1 Newton, I should just see this thing slide a little bit and then bend downward. Now for the mesh, I'll use a coarse curvature-based mesh. That'll keep things running fairly quickly. But I will refine the mesh a little bit in this contact region. This is the region where I'm primarily concerned about the results. So I'll apply mesh controls onto these few faces that I have here. I'll even tighten up that size a bit instead of the default 0.05. Maybe I'll try a 0.02 and see what it looks like. To me, it doesn't look too bad. I get about 2 elements across this 90-degree arc there. Okay, so this might be a decent compromise between sort of accuracy and solve time. And then one more important thing I'll turn on. I'll make sure I turn on this checkbox that says large displacement. And while I'm here, I'll change the solver to direct sparse. It tends to be more stable when you have a lot of sources of nonlinearity. But one more, I'll mention that this large displacement checkbox, that allows me to incorporate the geometric nonlinearity, an important aspect of this problem. So with that, I should be good to attempt to run this study. I'll go ahead and click on Run. I'm looking at the mesh here too. I'm like thinking, I should probably refine the mesh there so I have more than just one element through the thickness in this critical region. But I'll start it off this way. Hopefully it just runs pretty quick to give me a rough idea of the kind of behavior. But that is something I would consider changing, is the mesh in this region. So it ran, and if I maybe animate the result, you can see a little bit of that sliding behavior there. So now I could rerun that study applying 2 newtons, 3 newtons, and so on and so forth. Let me show you. If I bump it up to, remember the hand calc reported the result was around 10 newtons? If I bump this up to like 20 or something, I wonder what happens. If I go with too big of a force. So this incrementer here, this is actually applying 10% of the load right now. So that's 2 newtons it's trying to apply. We're trying to do 20. Right now it's trying to apply 2 newtons. Looks like it was successful. Now it's jumping up to 60%. So this is up to about 12 newtons of the load. Ooh, and then you start getting errors. It says the strain's too large, you want to restart. So when you start getting these error messages, that might be a bad sign of it failing to converge to a result. With the large displacement option enabled, if I hit yes to restart, you see it kind of backtracks. Now it's trying to do 22.5% of the load and so on. And so here it should be successful at doing that much. That's only like about 4 newtons worth, which we have to get up to around 10, it looked like, according to the hand calc, for this to start having issues. Let this go for a bit longer, show you the general behavior, and then what I'll show you in the end here is how we can set up something called a design study that will automatically change the load repeatedly and rerun the study, and it'll report your displacement results to you directly, to where we don't have to rerun the study like 12 different times. As a matter of fact, maybe while this is even going, if I minimize that. So I've set up a design study, and you can see here in this design study, I'm testing out 10 newtons, 11 newtons, 12 newtons, 13, and then something seems, you can look at the displacement numbers I'm getting each time, sort of growing, and then something funny happens at 13, 14, 15. If I look at the graph, see that as I increase the load, the displacements increase, and then something weird happens. I increase the load a little bit more, and the displacements, they like dropped. So the problem is the study fails at some point, where it fails to actually run to 100% completion. So here it's actually applying a much smaller load. It's kind of like it ended up applying like 20% of the load, and then it said, or maybe like 60% of the load or something, and then it said, at 100% I couldn't do it, so I dropped it back to 60, and here's your result at 60%. Okay, so you can tell when a study failed when you see this sharp drop. Okay, so it looks like the study works at around 12 newtons. Works at around 12 newtons, but when we get to about 13 newtons or set 4, that's when it starts failing. So according to this study, it seems like it takes somewhere between 12 and 13 newtons to get this thing to start snapping into place. That's where we get an instability, and the thing just starts sliding off into outer space. So you see it's still struggling. I'll let it go for a bit. So here's that same kind of summary, a little more detailed summary where I'm starting off at 1 Newton, 2 Newton, 3 Newton, and so on. So you see the result sort of goes up linearly up to a point when we start hitting that curvature, probably that curved region there. So it's going up in a different kind of linear curve. But right about 12 to 13, we see that it starts dropping off. This occurs, if I look at the result at the 12, it's right, the contact point's right about there when it finally doesn't take any more force. It actually starts taking less force to get it to slide further. Okay. So next what I'd like to do is maybe show you a nonlinear study, something a little more direct. Rather than having to set up that design study to run it like 15 different ways, 15 different times, we can be more direct and just run it once and get all the intermediate results along the way. And there's different techniques we can use to keep it stable along the way too. So if I set up a nonlinear study, let's set up a brand new nonlinear study on this. What I can do is copy over a lot of that stuff that I already did in that static study, for example, or let me just grab one of these previous static studies. And I'll just drag and drop all the setup I did from earlier. I'll just drag and drop, or let me just grab all these folders and the mesh while I'm at it. If I could grab all that and drag and drop it into the nonlinear study, makes a copy of all that stuff, but I do want to change the material. And the material I want to use a nonlinear material rather than the linear one that was in those studies. Ooh, so that study that we were trying to run here finally says it failed after 5 trials. It's probably trying to do like 50% of load or something bigger, and then it couldn't and had to backtrack and still failed. Okay, so at 20 newtons, it's no go. 20 newtons is too much. Okay, and that's the kind of failure I'd get when the design study actually reports that last displacement. That's what that study was about to report to me. So anyway, back onto the nonlinear track here. I'm going to apply the nonlinear material. In this case, I have a material that's set up with a bilinear stress strain curve to mimic that acrylic. So in other words, it's got that initial elastic modulus of 3000, but then when I hit a stress of 45 megapascal, it'll use this tangent modulus of 300, about 1/10. So it softens. It softens once it hits 45. Now again, you can enter in your own stress strain curve, full curve, rather than just using this. But this is like a bilinear curve. So I'll apply that material. I'll get rid of that global contact again. And now what you can do in addition for the setup here is, instead of doing it as a force, usually with these nonlinear studies, it's more effective and more stable to do it, apply your load as a fixture. So in this case, I'm going to apply a 0.6 inch displacement. Because what I can do with that is I can measure the amount of force it takes to apply the 0.1 inch, 0.2, 0.3 leading up to the full load, to the full 0.6. And now 0.6 inches is not from here way out to here. 0.6 is just enough to push this thing underneath, just to see that initial interface. Then I'll go into the study properties as well. And here we only had this large displacement option with static analysis. However, in nonlinear, we can turn that on as well as control the solver to a much larger extent rather than just having to rely on the automatic controls. Here as well, I'll change the direct sparse, and I could tell it to use 2% increments. So that way it'll apply 2% of the load, then 4%, then 6%, then 8%, and so on. So to use nice small increments, so I can get I'll have basically 50 frames on an animation if I want to play it back or something along those lines. Now this study does take quite a few minutes to run. I think it's about 10 minutes or so if I were to use a similar mesh to what I used a moment ago. So I'll show you what the final result of that setup looks like. And actually, I didn't have to place the thing in contact initially. Since I'm doing this as a displacement, it's stable initially, so I don't have to take that extra step. So here I have that gap initially. And let me show you the animation. The animation it mirrors the results. I have it turned on so to actually mirror the results over, so you can see like the full-blown results, not just the quarter model. All right, so you can see the bending behavior. It's stress. This larger stress is near the little corners here, where it's the most rigid on the component on the right. Okay. We can also look at contact pressures. me show the deformed pattern of that, show the interface there. And I'm trying to look at the contact pressure where it hits its maximum. So if I go back and show you, there's a difference between where I thought, according to my hand calculation, where I thought the maximum might be and where it actually came up with a maximum. So if I show this sketch here, see, I thought the maximum would be right about here according to that little triangle sketch, but actually it's up here. Why the difference? How come I was off by that much? Well, if I go to the deformed result and kind of toggle back and forth for a moment, you see a couple effects. One effect is that you can see that this thing, when it bends downward, this face, I mentioned this earlier, the face tips a little bit. So that perpendicular direction that I was using this to make it perpendicular to this edge, I mean, that direction changes a bit. So it messes with one of my assumptions. Another thing is this thing deforms upward a bit too, so the angle of this changes. So those together, okay, you can see it looks like this is nice and perpendicular to that edge, whereas when I turn off the deformed shape for a moment, you can see it doesn't really look perpendicular when okay, so it's like the post-deformed shape is what I really should have used this sketch based on, but how would I have figured that out? That would have been a little trickier, okay, as with the hand calculation anyway. So it looks like I'm expecting the forces to be larger because of the fact that we had to push over this bigger hump, so to speak, than what I was estimating down here. Let me evaluate those forces though. If I use the list result force tool, grab this back face, this is the face where I fixed, and then ask for the curve. You can see the force required. It increases, flattens out right about there, and reading down here in the bottom looks like about 11.4, 11.3 ballpark newtons. Okay, it was when it hits its maximum, theoretical maximum, and then it starts decreasing from there and drops off. So 11.3 ballpark it looks like. So this graphic shows a couple things I was just pointing out there, how my hand calc didn't really match up with the nonlinear simulation. Should get more accuracy out of the nonlinear simulation. And also the fact that I'm accounting for material nonlinearity, that tangent modulus, and so that should soften the material as well. So there's a couple of effects that I'm able to take into account that I wasn't able to prior. So comparing the answers from all these different studies, our hand calc predicted around 9.8. SimXpress 8.6, but somewhere between 12 to 13. We could have narrowed that one down a bit better if I did a more thorough design study. And then with the static analysis, and then 11.3 with the nonlinear analysis. This is the one that I don't have a physical test to really compare, but this is the one that I think makes the fewest assumptions. So I think it's likely the one to be the most accurate, has the potential to be the most accurate out of all these studies that we've run so far. So with that, that concludes this presentation. Let us know if you have any questions. Feel free to shoot me an email. Here, let me put my email on the blank slide here. Okay. So again, feel free to shoot me an email. My email address is sean@decisolutions.com. Let us know if you have any further questions regarding any of the assumptions and setup of these studies, or if you just have general questions about nonlinear or training or etc. Thank you for coming.